Hello, my name is Dr. Eric Landrum from the Department of Psychology at Boise State University, and you're watching my screencast about Between Groups Designs. We're in the midst of our Research Methods course, and this is a very important component. In fact, at the beginning of this lecture, we're going to start off with the four basic building blocks of all experimental designs, and then we'll dive a little bit more deeply into between groups towards the end of this screencast. So there is a shorthand that we use, and I wanted to kind of give you the code first before we start using the code in that shorthand way. And so when you see in the following screens R, that stands for random assignment. We talked about that a few screencasts ago, whereas we've drawn our population from the, I'm sorry, we've drawn our sample from the population, and now from that sample, we're ready now to randomly assign. So R stands for random assignment. X is the experimental manipulation. That's the experimenter applying the independent variable. That might be an intervention, it could be a control group, it could be multiple types of interventions or experimental manipulations. The O is going to stand for observation, or that's really the measurement of our dependent variable. And so you'll see an OXO design, and we'll get into that here in a moment, and there are names for that. But if you understand what these letters stand for, then the designs, as you're going to see them, are going to make a lot more sense. So that O, whenever you see it, means that we're taking a measure. It's either a quantitative or qualitative variable, but we're taking a measure of our dependent variable. M in the slides coming up here are going to stand for matching. And so just to get us started, so you see OXO and you read it in a line from left to right. And so this would be a situation where there's an observation, then there's an experimental manipulation, an intervention of some sort, followed by another observation. And so we might call this pre-test, post-test. Sometimes you'll hear it called before and after. So I think the classic example of this would be a weight loss study where you're enrolled to be in a weight loss study. You do your weight at the beginning of the study, and you do something for weeks or months. That's the X. And then at the end of the study, you weigh on the same scale in the same way. And so that would be a pre-test, post-test. If you saw just the X and the O, that would mean a post-test only. And probably a good example of this, and of course there's hundreds, if not thousands of examples, would be you're enrolled in a course at a college or university, and at the end of the course, you're going to do an evaluation. So you can think of the course as the X, the experimental manipulation, something's being done, and the O is the measurement of the effectiveness of that course. And so you'll hear this called a post-test only design, or sometimes just after. So remember that top line, OXO, pre-test, post-test, or before and after. And XO is the post-test only or just after. So again, remembering those four letters there will help us with the shorthand for what's to come. And I do really think they're like Lego building blocks, and you're going to see how they go together in different permutations and combinations. As I mentioned at the outset, there are four basic building blocks to all experimental designs. And you can see here in the corner of the screen the Mark Wahlberg research meme that I've been mentioning to you about. And here's one that cleverly includes a control group reference. So one of the four basic building blocks is right here. Either the dependent variable is measured before and after the experimental manipulation or just after. In fact, we've just gone over that in the prior slide, and I gave you these examples of pre-test, post-test, and post-test only. And so one of the things about experiments you need to know is the DV measured before and after or just after. So that's one of the four basics. A second basic building block of all experimental designs, each group in the study either receives only one level or combination of the levels of the independent variable. That's called between groups or between subjects, sometimes you'll see. Or each group receives all levels or combinations of the independent variable. That's called within groups or within subjects designs. Okay, so a couple things. At the end of this little section on the basic building blocks, we're going to spend the rest of this screencast on between groups designs. And then if you're watching these in order, the next one after this screencast is all about within groups design. So you're going to get a healthy dose of both. And by the way, there can be a combination of these combinations. So let me give you a between groups design. It means that we're going to test our hypothesis on different groups of individuals. And so if gender were an independent variable, then gender would have two levels, and that would be a between groups design because we're going to look for the difference between a group of males and between a group of females. All right. Or it could be, for example, your preference for ice cream. And we want to see how much you enjoy your favorite flavor of ice cream. And I could use that in a between groups design where one group gets chocolate, one group gets vanilla, one group gets strawberry. And so I have three separate groups of individuals. They get one flavor of ice cream. And that would be an example of between groups design. Now, not to complicate this too much, but I just want to give you a quick example, although the next screencast goes into it much more deeply. Within groups designs would mean that a person in the study gets all levels of the independent variables. So to go back to so for example, gender is not a variable that can be tested in a within groups design. However, ice cream could be, and so rather than having three groups each getting one flavor of ice cream, I could have one group of individuals getting all three flavors. And so I might have you taste chocolate, take a pause, taste vanilla, take a pause, taste strawberry, take a pause, and then evaluate each one of those two on the dependent variable. And so some variables can switch between and within, and some really can't. And that's all about whether it's a subject variable or a non-subject variable. And we will circle back to that here in the next few screencasts. And so that's another one of those basic building blocks. A third basic building block of all experimental designs is either there's one independent variable or there's more than one. And that's pretty straightforward. And when there's more than one, we have a special name for that. You can see it on the screen. It's called a factorial design. So that's pretty straightforward. And so you've got one independent variable or more than one. And by the way, as we get deeper into this and we talk about this together as a class, you're going to find out that the more interesting experimental designs typically include more than one independent variable, because more than one independent variable gives us a chance to look at interactions and how different variables can interact or influence one another in sometimes very unique ways. And again, we'll get into that as the semester progresses. The final building block here, oops, I'm sorry, looks like I've got an example here for you. So, by the way, if you have both a between groups independent variable and a within groups independent variable, you could call that a mixed factorial design. So if I was testing gender as one of my independent variables, that's between groups, but I was doing ice cream as within groups, that is, I'm giving each person vanilla, chocolate, and strawberry, that would be actually a 2 by 3, 2 levels of gender by 3 levels of ice cream. The first is between, the second is within. That's a 2 by 3 mixed factorial design. It's mixed because we have both between and within, and it's factorial because there's more than one independent variable. And in that little scenario I just played out for you, the dependent variable might be a preference rating or a taste buds rating or something like that, some sort of measure of favorability. All right, so here's the last building block of experimental designs. Those subject variables are controlled by randomization, matching, or blocking. All right, so, and I've talked about this a couple different times in different screencasts. So subject variables are these traits, qualities, and characteristics that each of us carries around with us. And so if you think about yourself, or you think about me, you think about you, you have an intelligence level, you have an IQ, you have gender, you have age, you have ethnicity, you have cultural background, you have height and weight and hair color and eye color. And so remember our definition of independent variable. I can manipulate, I can control, or arrange. We can only arrange subject variables. And so I can only arrange people by their IQ. I don't randomly assign people to IQ groups. I can only arrange people by gender. I don't randomly assign people to gender categories. And so when we're talking about those subject variables in our experimental designs, we have these three options. We can either randomize when possible, we can match, or we can block. And so randomization is our preference, but it's not always doable. So for example, we've talked in a prior screencast that it's very difficult for me to randomly assign college students to sections of a course. So I might have to use different techniques. One is matching. We're going to cover that in this screencast about between groups designs. And the other one is blocking. And I'm going to talk about that one in the next screencast about within groups designs. That's the fourth of the four basic building blocks. And this note right here is kind of important. Just because you know about one doesn't mean you know about the other. So if I tell you you've got a factorial design, that doesn't tell you about between or within. Factorial just means there's more than two independent variables. If I tell you it's a between groups design, that doesn't tell you about how subject variables are controlled. And so if I tell you about between, it doesn't tell you anything about randomization, matching, or blocking. And so there's four different components there, but remember, just because you know one doesn't mean that you know necessarily any of the other three components. All right, so let's jump in and take a deeper dive into the rest of this screencast into between groups designs. So I'll typically talk about between groups with two, but you should really know from the onset it can be any number two or above. Two or more groups of participants are used as points of comparison to evaluate the effects of the independent variable on the dependent variable. You can see a little graphic here that I pulled from the internet. And this is kind of the basic, fundamental, the easiest example to wrap your head around. So you've got that population, you draw your sample using random selection. Hopefully that sample, and that's in that dotted box there on the graphic. You've got your sample, and then you're going to hopefully either randomly assign or use matching or use blocking to have group one and group two, and those two groups get treated differently. And that differential treatment is the essence of the independent variable manipulation. And so again, you see two groups here. It could be three groups, it could be four groups, it could be five groups. I might do a study about the effectiveness of advising practices with freshmen, sophomores, juniors, and seniors enrolled at a college or university, and so that would be a four-group design. So when we talk about between groups, I'll typically talk about two as the easiest example, but just put a note in the back of your head that it doesn't have to be limited to just two groups. So the effects of the independent variable are called treatment effects sometimes. And so maybe the beneficial effect of that advising practice, or maybe if you're in that weight loss program, that would be the beneficial effect of the weight loss regimen or the protocol that you're following to lose weight. So here's an example of, it's called CRD, a completely randomized design. And here we're using our shorthand here. We're using our nomenclature. And so again, you read from left to right. And so that order makes a difference. And so what that means is that we'd have two groups because there's two rows. And the first group, on the one on top, they're randomly assigned. And then there's a pre-test. And then there's the intervention, and then there's a post-test. That second row is really acting like a control group. They're randomly assigned. There's a pre-test, nothing happens to them, that's the control, and then there's a post-test. Now, even though it's blank, they might do something there. It might be a placebo condition, so you'd have to really dig in more into the details of the study. So it's a very clean design. There are some drawbacks to every type of approach. There's no approach that's perfect for every scenario or research situation. So some of the general drawbacks are test sensitization and different scores on the dependent variable. So let me cover each of those separately. So test sensitization. So let's say, for example, that I'm going to offer you a prep course for the graduate record exam for the GRE. And before I offer that prep course, that's going to be my X, my experimental manipulation. I'm going to give that to half of my participants. Half my participants are not going to get that. If I give, so look at the top line again. So ROXO. So I randomly assign. Then you're going to take a GRE as a pretest. You're going to take my GRE test prep course, and you're going to take the GRE again. Then I'm going to have that second row is going to be my control group. Well, test sensitization is the issue that taking the GRE the first time might alert you to what it's going to look like the second time. And so I'm going to be curious about, will any increase from pre to post be because you've just seen the test before, or is it really because of the effect of my prep course? And so that's the issue there. The other part of it is different scores on the dependent variable. So you can actually subtract, you could take the post minus the pre and get like a gain score or a delta score, a change score. Now, that'll work okay if both the pre for the experimental group and the pre for the post are roughly in the same place. They're roughly equivalent groups, but sometimes when you take different scores, you might actually hide where the starting points are. And so you have to be a little bit careful about that. Sometimes a different score could be beneficial, but sometimes it actually could be hiding things that really aren't there. And so, however, if you want to try, if those are important drawbacks and you want to try to get rid of that, well, there is an alternative. You could use a completely randomized post-test design like you're about to see, post-test only design, which you're about to see on the screen. And so there you go. So if you're worried about the test sensitization of the GRE, the pre, well, look at it, it's gone now. You're randomized. Half my participants get the GRE test prep course. The other half get get nothing, but they both get the GRE at the end of the session. So now I've gotten rid of test sensitization. Now I've also gotten rid of any difference scores because I'm not subtracting pre minus post or post minus pre. However, like any other design, there are going to be drawbacks. But now you got to worry about equivalent groups. In other words, randomization is typically good, but it's not perfect. And even by random chance alone, we're going to have differences between different groups of people in a study. That's just the nature of experimental research with human beings. And so sometimes, if we're not completely confident in randomization, we have other tools in our tool belt, and that's where we're going to talk about matching here in a little bit at the end of this screencast. And we'll talk about blocking in the next screencast after this one, if you're watching them in order. So you've got some options here. If you really want to know about where the group's equivalent before I started, or roughly equivalent, this would not be the design choice. But if you're worried about test sensitization, I don't want my participants to see the GRE twice, well then this would be a nice choice to eliminate that potential drawback. So randomization is good. It's not perfect. It tries to control for extraneous variables. It does a good job, but not always great, depending on the scenario. So here's where I want to introduce this notion of matching. And in our shorthand, we're going to depict that by the capital letter M. So matching allows for this control. So let's say, for example, I was going to draw a sample from the registrar, and I wanted to get GPAs of students, and I want to do a study where GPA is going to be one of the key variables, or I think it may be one of the influencing variables in the study. And so it looks like I've got a list of 20 students here. And so I go to the registrar and I ask them for a list of students, and here's my sample. And then in theory, I mean, again, this is kind of a little bit out there, but in theory, if I flipped a coin, it might be that it ended up with all the ones in red are in my treatment group, and all the ones in black are in the control group. And you can see the solid red line separating those two. That would be bad, because now my groups are different before I even started my study. So randomization is good. It oftentimes works just fine, but sometimes, and especially in a small n situation, it's not going to be perfect. And so this actually could, in theory, happen. So I get my 20 people, I randomly assign, I flip a coin, and maybe I get 10 heads in a row and 10 tails in a row. That would be unusual, but it could happen. So, if I want to avoid even a smattering of that possibility, I could match. And so what that is like is that you have the same rank ordering, and I've tried to depict this for you in the graphic on the right here. So I've still got a 4.0, a 3.9, a 3.9, a 3.8, and so forth. I've got them ordered, but then you can see I've drawn the circles. I've matched the closest possible pairs I can based on this roster, and then I randomized. And so I circled the 4.0 and the 3.9 at the top. That's my matched pair. I flipped a coin. Heads, you're in the experimental group. Tails, you're in the control group. So notice, by the way, so I'm matching first, and then I'm randomizing. And the notion here is that each person, for true randomization, should have an equal chance of getting into either the treatment group or the control group, the experimental group or the control group. And so you can see that they still do. It's still a 50-50 chance. It's still a coin flip. On the left, it was a coin flip, but there was a sequence of coin flips that could turn out really disastrous for us. But on the right, I'm still flipping a coin. Each person still has a 50-50 chance, but now I've constrained it to the extent that I'm going to be, I'm going to be roughly equivalent. In fact, if you took all the GPAs in red, on the right, and all the GPAs in black, I'll bet you that you come out to be pretty close to equivalent on those means for that group. So here are a couple of matching designs. And so I could match, then randomize. You saw that on the prior screen. And then I could do a pre-test, post-test, or I could match and randomize and do, that's my control group, sorry. Or I could do a post-test only where I match, then randomize, then the XO, and then I could finally do my control group where I match, I randomize, and they just do the dependent variable observation where I'm measuring the dependent variable. And so the matching, hopefully that makes sense to you. You're still randomizing from the matched pair, Everybody still has that 50-50 chance of getting into each row if you're only working with two conditions of your study. And now the variables that you think influence your study are being controlled for a little bit more. And I kind of want to summarize that here for you here in a moment. So, just to kind of recap, you can match on more than one variable. My example was just GPA. There are studies in the literature that match on 5 variables. You can see one example here: sex, age, education, social class, and IQ. But hopefully, if you start thinking about that, you can imagine if I wanted 50 matched pairs on those 5 variables, it might take me a couple thousand participants to actually get the 50 matched pairs of sex, age, education, social class, and IQ. So you're doing a lot of work up front, but you're going to get a nice clean test later on. In fact, it's almost like 2 studies. You've got to do one screening study to get your matched pairs, and then you do your real study where you have your treatment group and your control group. The example I gave you a couple of screens ago was GPA. That's just matching on one variable. That's pretty straightforward. But imagine the complexity of trying to match on multiple variables. It's just going to take a lot of time and effort. So you can see the value there. It reduces the likelihood of error, increases probability of equivalent groups on those critical correlated variables. Now, of course, you're going to have to dig into the literature and know which variables are critical or correlated with your dependent variable. So it makes much more sense, psychologically speaking, to match on age and education than it does on hair color and birth order. And notice the matching, these are subject variables. I carry around my age, my education, my hair color, and my birth order. So you want to do your homework and you want to understand what variables might influence the outcome of your study that you may or may not be necessarily interested in. They could be confounding, extraneous, or nuisance variables. So when would you use matching? You might use it when sample size is small and equivalent groups might not be guaranteed so much through randomization. Remember, randomization is good and it works pretty well most of the time, but a small n, with my 20 participants in my registrar study, I could get 10 heads and 10 tails, and then I'm really in a bind with regard to having roughly equivalent groups before I do my study that's related to GPA. Again, another part of that is that you only want to match on things that are relevant to your study. So if there's some significant correlation or relationship between the subject variables and the dependent variable, that's going to be the time that you want to match. And so here, I'm just going to reiterate that again. Now, the key thing is here, how would you figure that out? You figure that out by doing a literature review, by using your PsycInfo database, by reading journal articles about the same topic or the same variables as yours that you've selected for study. That's how you're going to figure out, should I do matching here? Is that going to be a relevant characteristic that I'm going to have to pay attention to? Or is it going to be okay and I don't have to worry about it? All right, well, that's it for the 4 basic building blocks and a little bit of a deeper dive into between groups designs.